So, hello everyone. My name is Andrew, and I work at Intel compiler team. And we have been working on a SYCL compiler for quite a while now. It's still a new project for us, so we would like to share with you about what SYCL is and what was our journey in implementing the SYCL compiler. So we're going to start with what is SYCL, and we will continue and write a simple program in SYCL, try to understand the concepts of SYCL and how the programming of the SYCL works. Then we will take a closer look at the key features of SYCL that are unique to SYCL and how they can be used to improve your programs. And then we will talk about the implementation of SYCL compiler, basically what we need to make in order to bring SYCL compilation to Clang and what we already have in our implementation. And we conclude with our upstream plan. So we are developing the SYCL implementation in order to contribute it to LLVM work soon. So I hope that this talk will give you an understanding of what we're trying to bring. So here's a slide contributed by Intel Legal. And now, when you're ready, let's get started. So, like heterogeneous programming, what is it? Like, SYCL is a language for heterogeneous programming. And back in the days, like the classic programming languages were designed to support writing programs for a single device, like writing programs for CPU, and that's it. Nowadays, like we have not only a CPU, we have different devices. Your laptop probably have a GPU. You can have an FPGA boards in your server room. So you need to find a way to program all these devices, and you probably don't want to learn another language for each of these devices. That would be, well, inefficient for a programmer. So SYCL aims to solve this problem and aims to provide an abstraction layer that you can write programs, the heterogeneous programs in C++ without extensions. So just writing pure C++ and get the code offloaded to a device. So let's see how this works. Let's see how the programs in SYCL look like. And yeah, let's take a toy example. Let's code a program that sums two vectors and put the result in a third vector. We have a declaration and accepts a templated parameter, so it works on any type. So in order to use SYCL, we first want to let the SYCL runtime know about our memory on a host. So we create SYCL buffers, and these buffers will represent our memory on both host and a device. So this is kind of a single buffer that represents both host and a device. And next we create a device queue. So this device queue will be used to push our work that we want to offload to a device. And this queue, well, it is asynchronous first because communication with the device can take a while, so we don't want to block your C++ code. So, and the second thing is this queue is it's out of order, and it's a really great property that we are going to discuss in a minute. But for now, we have this device queue, so let's submit an operation. We call device queue submit and specify a lambda to it. And this lambda is actually a description of the operation that we want to submit, like to let the runtime know about what's going on in this lambda, in this code. And the first part of the description of the operation is accessors. And this is basically an input and output buffers that the operation will operate on. So we get access to buffer A and B for read because we are going to read them, and buffer C where we store a sum of two vectors will be our output buffer. The next thing we want to call a parallel for, which will iterate. Well, not iterate. Will go over the range that we specify, and the range is like a whole vector, and we. And the body of this for loop will be the lambda that we pass in. So the lambda will be executed on all items of our vector. So let's write a code of a lambda, and that's it. Yes, we compute sum of element-wise of two vectors. And actually, that's it. So you may notice that there's no synchronization explicitly written by the programmer. So we just write this code, and we exit from a function, return from a function. And what happens is the SYCL runtime, well, it employs a RAI technique. So when the buffer C goes out of scope, you will get, so the SYCL runtime will transfer the buffers to a device, will run a computation and get the result back, and ensures that the data will return to vector C. And this is without like user interaction. We just call submit and do our stuff. Okay, so the runtime is pretty smart, and it will transfer the buffer. It will not update it if the buffer is not being written to. So so this is the first feature of the runtime. And the second feature is more complicated. Like in the previous example, we had a single kernel invocation, the device kernel invocation. But what happens if we have several kernel invocations that happen to work in the same buffers, happen to share something? So again, same example, we had two buffers input, one buffers output, and so far so good, but then we submit another operation. And this operation happened to use the result of the first operation. So we have a data dependency between two kernels. And in many heterogeneous frameworks, you have to synchronize it manually. But as you can see, there is no explicit synchronization. And the actually runtime builds a graph of all operation. It tracks the memory dependencies, it tracks the input buffers, output buffers, takes access type into an account, like if the read and write, read-write access, and so on. So the runtime schedules this graph properly, so there is no conflict with the data-dependent kernels. And if there is a possibility to parallelize the work, the runtime will attempt to do that. Now, the single source. This is another great feature of SYCL, which better be explained with example of a framework that do not have single source model. And for example, OpenCL. Well, in OpenCL, you write a code in two files. One file is for host, another file is for device. You compile them with two separate compilers, and and you put this into files. So, and this works pretty well until you try to exchange data between host and device using user-defined structures. So, for instance, here we have a struct point. We have two chars on both a host and a device. You usually put this in a header file that is shared. And the problem is this doesn't work, actually. And the reason behind this is that we have two compilers. One compiler compiles the host, another compiler compiles the device. They have different, even LLVM versions. One may not be LLVM based at all. Like they make different decisions on what layout of the structure to make. So it's undefined. And if you try to do this like trivially, it will not work. Your program might crash, and a lot of people complain about this. And the solution is simple. You can put an attribute packed for a struct and make a padding manually, but you have to do it for every single struct that you use in your program, for nested struct as well. So it's a lot of work, and it's not really convenient. So you have to be really, really careful with a complex data type that are crossing the border between the host and a device. With SYCL, we don't have this border. We have a single code with a single source model. We have a single type declaration, and we have a compiler that is aware that there is a host and a device. So the compilers are implemented in a way that they produce a compatible layout for user-defined structs. So this example just works. So the compiler ensures that the layout is the same, so you can use your type system from a host on a device, and so you actually have a single type system. Now, so this is the tour for the features of SYCL. Let's talk about how this gets compiled, how we implemented at least the compilation flow. So first, let's see what's the difference between standard C++ flow. In standard C++, you have a CPP file that you compile with a compiler of choice. You get an object file from that, and you link it with a linker, platform linker, with other object files and libraries and so on. So you get an executable file. Now, what SYCL brings to the table? So we have two options, two extra options. One option turns on the compiler features of SYCL, and another option, -lSYCL, turns a linker, it links with a SYCL runtime, a small runtime. So the compilation option -fSYCL does all the magic underneath. So it is not exposed to the user. So the user only have to add one option to a compiler and one option to the linker. So let's see what a -fSYCL does actually. Well, the Clang driver has a complicated implementation of -fSYCL. It basically has two flows. Like on the left, you have device compilation flow, and on the right, we have a host compilation flow. So we kind of compile the same source twice, one for device. We extract the kernels, basically the lambda that is passed to a parallel for, and we compile that. So we will leave only device code in the device LLVM IR, and then we invoke the compiler that is specific for your device that allows you to compile LLVM IR to whatever device you use, like GPU or any other device, CPU maybe. So you get a device binary from device compilation. Now, getting back to the host compilation, it's still simple. It's almost the same as a standard C++. You get an LLVM IR, you get an object file, and then we don't want to carry this device binary along with our program. We actually want to bundle everything together. So we have only a single executable that just happens to work on a GPU or CPU or FPGA or any other device that we want to support. So we bundle everything together with an object file, and then just link this object file with the SYCL library and other libraries that we want to get an executable that is capable of running on a CPU, on a host, basically, and on a device. Now, so in this picture, we invoke a device compiler, and this could be many different compilers. So typically for different GPUs, CPUs, and other accelerator, you have different compilers. And the binaries, of course, will not be compatible. So you have to recompile your program for each of these accelerators in order to run them. And it's not always a good thing. What you can do instead, you can, instead of creating a device-dependent binary, you can create a SPIR-V binary. And yeah, what is SPIR-V? Some of you may know this, but SPIR-V is another standard from Khronos, which are a company based on OpenCL, OpenGL, and SYCL. I forgot to mention that, but anyway. So SPIR-V this is like a intermediate representation. It is a portable, like a device-agnostic intermediate representation that is originally implemented for OpenCL and Vulkan. And so if you carry this SPIR-V binary instead of like device-specific binary, you can actually have an executable that can run on any supported platform, a single executable that can run on different accelerators. And this is useful because you may not control the environment in which your program will run. Like if your users have like AMD GPU, ARM GPU, Intel CPU, you don't want to compile separate executables. We want to compile one executable and run it everywhere. So SPIR-V is, well, there are a lot of devices that support SPIR-V already. And for our SYCL compiler, we currently use SPIR-V LLVM translator, which is a library that allows you to convert LLVM IR to SPIR-V and vice versa. There is an ongoing discussion on merging this SPIR-V library into LLVM tree. Hopefully this will happen at some point, and because SPIR-V is really nice if we want a device agnostic IR, and you don't want to tie with the LLVM versions because SPIR-V is a stable interface. Now, let's discuss another thing that we implemented. So how the device code and the host code actually interact. So in the CPP file, we have a parallel for and a lambda inside. So the device compiler extracts this code and makes it in a device binary. So what host code needs to do? It needs to take this device binary and create a kernel. For example, here we have OpenCL backend. There could be another backends. But to create a kernel, we need a kernel name, and we need to set up parameters. And actually, these accessors are captured by the lambda. They are making its way to the kernel parameters. So we need to get these accessors from a lambda and set it as an argument. So the kernel name problem is the kernel name is specified by a user-defined class. And in C++, you cannot get a C string from a type. You just cannot convert kernel1 to a C string because it's a type. We don't have a static reflection in C++ yet. But anyway, there are non-portable things that we can use, so that's not a major problem. The major problem is actually the arguments. So you need to extract these accessors from a lambda and set it as an argument. And since the content of a lambda object is undefined, different compilers take a different path, it's difficult to do and difficult to get this offset from the lambda object. And so we're thinking what to do with this and found out that the device compiler is already aware of all this information. So it already knows the device, the kernel, it already knows the kernel name because it generated the kernel name in the device code, and it already knows the parameters of a lambda because, hey, we are compilers, we know what we put in the lambda. So what we do, we make the device compiler emit another output, which is an integration header. And in this header, we put something like a type trait for a kernel. So runtime can use this type trait to get a kernel name. It can use this trait to get argument numbers, where the arguments are stored in Lambda. So it's it's very useful and allows us to do this safely. And this kernel and this header is implicitly included for host code compilation, so the SYCL runtime can access this data for every kernel in a program. Okay. So everything you just saw on examples, all these classes, the accessors, the buffers, kernels, and all the stuff, all of this is a pure C++ code. It is implemented in header files, a lot of them. There's also a small runtime library that you have to link in. And there's a lot of headers. So it's just like a standard library. So what we are going to do with this next. So right now, all of this code is developed in Intel LLVM repository on GitHub. It is open source. You can access, you can see the code. but it's not the final destination of this code. Like our destination at LLVM work, we want to contribute that. We want to collaborate with other implementers in LLVM work, and yeah, so we sent a RFC in January describing the overall language. And big thanks to the community and the people who review and give their valuable comments on our implementation. So the first patch, first changes for the Clang driver, this -f SYCL stuff, is already merged. So thanks a lot. And yeah, we actually have a detailed plan for upstream. Like all the features are outlined and better described than I just did. But so take a look at this issue on GitHub. It has a document inside. We track it there. And yeah, the source code link. Please make sure that you check out the SYCL branch, not the master branch, because all the stuff is on SYCL branch. The master branch is just a mirror of LLVM on a repository. So yeah, call to action. So we are not planning to make an Intel specific implementation. What we're trying to make is a place and a framework where different vendors, different implementers can participate, enable their devices, and share the code as much as possible. That's why we go to LLVM.org. And yeah, please provide us your inputs for the design. It's a great time to do that because we're still changing the stuff that don't work, or we not really, so we don't really like some pieces. So your comments will be really, really welcome. And yeah, you can send a pull requests, raise issues, and so on in the GitHub repository. And yeah, and feel free to join us on the path to LLVM work. And then that's it for today. Thank you.
Questions?
Thanks for the talk. It's really glad to hear the works like open source and the Clang patch has been merged. Congratulations. But I'm wondering whether you open source or like plan to upstream some SYCL specific optimizations.
So SYCL specific optimizations. Okay, so the question was, are we going to open source SYCL specific optimizations? And the answer for this is, well, it's not trivial, I guess. The first thing you need to know is that right now we use OpenCL as a backend for SYCL. Like all stuff you just saw, it lowers down to OpenCL right now. It is possible to use different framework underneath, but right now we use OpenCL because we have a good OpenCL implementations for our devices. But so our optimizations lies in the OpenCL level, mostly. Like where the middle-end optimization reside, where the code gen for x86, for GPU, and so on. So as for the upstream, so we have a GPU runtime already available on GitHub. That's a full runtime is there. Our CPU runtime is currently closed source, but we actually will make it open source pretty soon to make it available for everybody. And yeah, we also have discussions with how to integrate the more OpenCL runtimes, more OpenCL optimization to LLVM work. And this kind of benefits the SYCL as well.
Yeah, but I mean that I see a lot of like opportunities, like because SYCL got a single source view on both host and device, right? So we can have somehow a lot of like global optimization, which is hard to be done in OpenCL. So that's the reason I asked whether there's like a SYCL. Yeah.
Yeah. So exploiting the single source model and getting performance out of this is a really promising approach. We are not there yet. We don't have any optimizations right now. We're still building a compiler. It's not like production ready, so we just tune the performance. We're actually developing things. And I assume someday we will make some optimization that works and it takes both host and a device into account. We'll figure it out.
Thank you.
Sure.
So if I have a completely heterogeneous system, let's say an ARM CPU, an Intel compute card, an AMD GPU, and maybe an FPGA to add on top of it, and then I throw a couple of tasks at it via SPIR-V code using SYCL, does SYCL have any understanding of what the available units are and what particular unit would be particularly suitable for a specific task? To make sure that, for example, a string handling task doesn't go to the GPU while a graphics task goes to the CPU at the same time.
Let me just get back to one slide. It's just the hello world slide. So in this example, we had a device queue, right? And maybe your question is related that we don't specify what device we're running for. Is this right?
Yeah, exactly.
Okay, yeah. So this is for simplicity. So this line will just take a default device for whatever default device understanding of the SYCL runtime, but you can specify and you can select the devices. So you can select a GPU, you can select a particular vendor of a GPU, so you can create a queue on some devices. Yes, so you can program in SYCL and use really heterogeneous computer.
And is there already some concept for automatically picking the right one for a specific task, or is that something that would have to be done in an add-on library?
We didn't work on this, like picking the right device. We still leave that for a programmer. I guess it makes sense to do it. I guess it's just difficult to choose a right device where the choice must be made. Like, in this example, we don't know what is going to be included, so we don't know what to choose, like CPU or GPU or something else. But yeah, so the fine-tuning from the programmers is of course possible. You can select everything you want.
On one of your slides, you've seen the invocation of Clang. It looks like it invokes Clang twice on the same source file.
Yeah.
So the entire parsing, etc., goes on a type source. Why not just having one invocation of Clang and emitting two LL files?
Okay, so the question is why we invoke the Clang twice and not using the same compiler invocation to compile both hosts in the device. Well, basically because we actually have different targets. Like our target is a host system, which may be x86, and another target may be a GPU. So you have different target information, you have different triple, and that makes things difficult to do in a single invocation. So we have a question here.
Oh, there. So all of that looks a lot like OpenMP.
Yeah. It resembles the OpenMP.
OpenMP target offloading works this way in Clang right now.
Yes.
If you download Clang, it does exactly this. If you look at the code, it is like a little different design choices, but generally speaking, it's OpenMP target offloading. Now, what do we need to do to actually make Clang do the same thing for both? Because I don't want to have like SYCL handling in there while I have OpenMP handling in there, while they basically do the same thing.
Yeah, okay. So the question is, can we somehow merge these flows between SYCL and OpenMP so we don't duplicate the things in the front end? And I believe the answer is yes. We're trying to integrate our SYCL flow or SYCL compiler changes with whatever else the community does. So we're trying to reuse as much as we can. For example, SYCL shares a lot with OpenCL, C++, like address spaces and other features are really, really similar. So we are trying to reuse that. And for the flow, yes, this is really similar to what OpenMP does. And we did not invent this. We were influenced with OpenMP implementation mostly. So I think it is possible. I'm not sure if it's done now, but I guess you can participate in a code review and suggest the.
Would be great.
Okay.
Maybe one more question. At some point you said you emit SPIR-V because it's a target independent intermediate representation, right?
Yes.
From LLVM IR, which is a target dependent intermediate representation.
Yes. Okay, so that's a good question. So I think in this picture I missed one important note here. So on the left side we have a device compilation, and the triple that we use for device compilation is a SPIR triple. Like it's not x86, it's not GPU's triple, it's SPIR triple. And the SPIR triple is used for OpenCL, and it is a device agnostic LLVM target. So the reason why we compile this SPIR triple to SPIR-V is that a SPIR triple is not compatible not portable between different LLVM versions. So you can have front-end compiler of the Clang like LLVM 9.0, and you can have your downstream consumer, their runtime on LLVM 5.0 because they still use 5.0. And you can't feed the SPIR from 9.0 to 5.0 because they're not compatible. It just won't work. SPIR does not try to make a stable API. We changed representation of types in SPIR a lot. And SPIR-V is the opposite of this. So it's a really stable standard. First of all, it's a standard. Like SPIR is not standardized, SPIR-V is. So it's a stable point, and you can actually decouple front end and the back end and use a SPIR-V in between. So one important note is that with SPIR-V as a device binary, you will have a JIT. You will have a JIT compilation for your device. And because SPIR-V is device agnostic, you have a concrete device, you need a JIT. And if you don't want this, you probably need a specific device binary instead.
Okay, we're out of time, so we have to take further questions offline, but let's thank the speaker first.